Hi friends, welcome to Math A to Z. Our today's topic is Wilson's theorem. This is from number theory, and the statement of this theorem is: if p is a prime integer, then p minus 1 factorial congruence to minus 1 mod p. P is prime, then p minus 1 factorial congruence to minus 1 mod p. That is p minus 1 factorial plus 1 congruence to 0 mod p. That is p divide p minus 1 factorial plus 1. This is the theorem. Now we try to prove this theorem. We consider an integer a which is in this range, 1 less equal to a less equal to p minus 1. Now if we consider the first p minus 1 multiple of a, that is a, 2a, 3a to p minus 1a. Here no two of them from this list are not congruent. No two of them are congruent modulo p. Why? Because if it happened, that is Ra congruent to A set, where 1 less equal to R less than S less equal to P minus 1, then R congruent to S, this is mod P, that is P divide S minus R. But from this condition we have this is impossible. Okay, so no two of them are congruent modulo P. That is we say that this p minus 1 integer are congruent to 1, 2, 3 to p minus 1 modulo p, but not in this order, may not in this order. Okay, because when you divide an integer by p, then it leaves remainder either 1, 2 or 2 p minus 1. Now if we take, since p is prime, then if we take any r belongs to this set, okay, then there must exist, if we name this set as S, there must exist R dash belongs to S, such that R into R dash congruence to 1 mod p. Also, if for any element R belongs to S, if R into R congruence to 1 mod p, if this holds, then we must have p divide r square minus 1, that is p divide r minus 1 into r plus 1. If p divide r minus 1, okay, then since minus 1, since r less than p, okay, so and p divide r minus 1, so this only hold when r equal to 1, that is r minus 1 equal to 0, then p divide 0. Also, if p divide r plus 1, this is also hold only if p equal to r plus 1, because p is prime and this implies r equal to p minus 1. Okay, so from this set, this element and this element are only two elements such that 1 into 1 congruence to 1 mod p and p minus 1 into p minus 1 congruence to 1 mod p, and the remaining p minus 3 elements, this delete, so there remains p minus 3 element. Remaining p minus 3 element can be paired. The number of pair is half into p minus 3 as r, r dash. Okay, such that r into r dash congruence to 1 mod p. So if we product all the elements of the type this, then we get 2, 3, 4 to p minus 2 congruence to 1 mod p, right? And this is p minus 2 factorial congruence to 1 mod p, that is p minus 1 into p minus 2 factorial congruence to p minus 1 mod p, that is p minus 1 factorial congruence to p minus 1 mod p, and this relation gives p minus 1 factorial congruence to minus 1 mod p, that is p minus 1 factorial plus 1 congruence to 0 mod p, or we say p divide p minus 1 factorial plus 1, and this is complete the proof of Wilson's theorem. Okay, now we see that for this theorem the converse is also true. Converse of the Wilson's theorem is also true, because so the statement of the converse is if p minus 1 factorial plus 1 congruence to 0 mod p or n, here also be n, then n is prime. Okay, to prove this, let b less than n be any positive divisor of, this is n, positive divisor of n. Hence d must be belongs to 1, 2 to n minus 1, since d less than n, imply d divide n minus 1 factorial, and this is let 1. And since n minus 1 factorial plus 1 congruence to 0, mod n imply n divide n minus 1 factorial plus 1. This is true. Since d divide n and n divide n plus 1 factorial, n minus 1 factorial plus 1. So from this we get d divide n minus 1 factorial plus 1. This is 3. And from 1 and 3 we get d divide n minus 1 factorial plus 1 minus n minus 1 factorial. That is d divide 1 implies d must be equal to 1. So we say that d equal to 1 be only positive divisor of n, which is less than n. So n must be prime. Okay, that is the converse of the Wilson's theorem is also true. So we say that if a number satisfies this condition, then the number is prime, and if p is prime, then p satisfies this condition. Okay, so the Wilson's theorem is the necessary and sufficient condition to test a number that it is prime or not. But this theorem is impracticable for the testing of primality, because if we take n be large, then n minus 1 factorial be also very large. So we face to find this factorial. So the testing of a large number which is prime or not is very laborious by Wilson's theorem. Okay, now we explain this theorem by a proper example. If we take a prime p equal to 30, then the number 1, 2, 3 to 12 we take from this to this and this can be deleted from the list, and we see that here 2 into 7 congruence to minus 1, congruence to 1 mod 30, 3 into 9 congruence to 1 mod 30, 4 into 10 congruence to 1 mod 30, 5 into 8 congruence to 1, this is also mod 30, and 6 into 11 congruence to 1 mod 30. Now multiplying all of them we get 11 factorial congruence to 1 mod 30, and 11 factorial into 12 congruence to 12 mod 13, that is 12 factorial congruence to minus 1 mod 13, that is 13 minus 1 factorial plus 1 congruence to 0 mod 13, whereas p equal to 30 is taken to be 1. Okay, this is the explanation of the Wilson's theorem. Now we consider an example. From this book, from Elementary Number Theory, David and Burton, to understand how to use Wilson's theorem in a problem. We consider this problem. Find the remainder. Find the remainder when 2 into 26 factorial is divided by 29. Okay. Here t equal to 29 prime. So by Wilson's theorem we get 29 minus 1 factorial plus 1 converse to 0 mod 29, that is 28 factorial plus 1 congruence to 29, that is 28 27 into 26 factorial plus 1 congruence to 0 mod 29. Right? Now we write this as this is minus 1, and in place we can write 28 because minus 1 plus 29 equal to 28, and we cancel 28 from both sides because GCD of 28 29 equal to 1, that is 27 into 26 factorial congruence to 1 mod 29. Now we get 2 into 26 factorial plus 27 into 26 factorial congruence to 1 plus 2 into 26 factorial mod 29. Here we add 2 into 26 factorial. Then here we get 29 into 26 factorial congruence to 1 plus 2 into 26 factorial mod 29. And since here 29, so this is congruence modulo 0, that is 2 into 26 factorial this here plus 1 mod 29, that is 2 into 26 factorial congruence to minus 1 mod 29, that is 2 into 26 factorial congruence to 28 mod 29. Okay, that is remainder is 28. This is the answer. Okay, thank you for watching, and we give the link of the PDF of handwritten note of this class in the description box. Okay, again thanks. Thank you very much.